Hello everyone, my name is Monit and in today's session we will solve 062541 of May-June 2020, that is paper 4 theory extended. Before going on, please read all the instructions mentioned in the paper, and before going on or watching this video, please attempt this paper and then watch that video, that it will be more helpful for you. Okay, now the very first question. An aeroplane of mass 2.5 into 10 raised to power 5 kg lands with a speed of 62 meter per second. So the mass is given and the speed of the aeroplane is mentioned on a horizontal runway at a time t equals to 0. The aeroplane decelerates uniformly as it travels along the runway in a straight line until it reaches a speed of 6 meter per second at t equals to 35 seconds. Now, in the A part, we have to calculate the deceleration of the acceleration in 35 seconds after it lands. So we know the formula for the acceleration, that is rate of change of velocity, that is final velocity minus initial velocity upon time taken. So we know that the final velocity after t equals to 35 seconds is 6. So v is equals to 6. Initially it was 62 meter per second, upon time taken is 0 to 35, that is 35 seconds. So we get minus 1.6 meter per second square. So here the negative sign denotes the deceleration, as it is already mentioned in the question, it is decelerating with a uniform rate. So the magnitude of deceleration is 1.6 meter per second square. Now in the second part, the resultant force acting on the plane as it decelerates. We know the formula for the resultant force, that is mass into acceleration. Mass is already mentioned, acceleration we have calculated in the first part. So just by putting up the values, we got the force as 4.0 into 10 raised to power 5 Newton. In the third part, the momentum of the aeroplane when its speed is 6 meter per second. So we know the formula for the momentum, that is mass into velocity. Mass is given, velocity is, we have to find out the momentum at 6. Putting up the values, we got the answer 1.5 into 10 raised to power 6 kg meter per second. Now in the next B part, at t equals to 35 seconds, the aeroplane stops decelerating and moves along the runway at a constant speed of 6 meter per second for a further 15 seconds. On this figure, we have to sketch the shape of the graph for the distance traveled by the aeroplane along the runway with respect to time from 0 to 50 seconds. You are not required to calculate distance value. We are not here to calculate the distance, but we have to draw the graph for 0 to 50 seconds for the aeroplane. So we know that during the first 35 seconds, it is decelerating. So the graph will be of curved nature as it is accelerating. So it will be decelerating, so the gradient will constantly decrease up to t equals to 35, and then after it is saying along the runway and then moves along the runway at a constant speed of 6 meter per second for further 15 seconds. So for a constant speed, we will have a straight line with a positive gradient. So that will be the curve. It will be curved for till 35, then it is a straight line till 50 seconds. Please remember, at this point the gradient will not be 0, the line will not be parallel, it will be having some gradient and then it will have the constant gradient from 35 to 50 seconds. Okay. In the last C part, the aeroplane decelerates, its kinetic energy decreases. As the aeroplane decelerates, its kinetic energy decreases. Suggest why this happens. What happens to this energy that we have to mention? So we know that if kinetic energy decreases because at its move along the runway, this energy is converted into thermal energy while braking or when it comes in contact with the tires and the runway and also with the air particles. So due to friction between the brakes, it is converted into, this kinetic energy is converted into thermal energy, in the form of braking with the tires or in the air. So this is the reason why this kinetic energy is being decreases and it is being converted into thermal energy. So we have completed the first question. Now the second question. This figure 2.1 is the extension load graph for a light spring S. State the range of the load for which S obeys the Hooke's law. We know that Hooke's law says that force or the load provided is directly proportional to the extension. So there should be a straight line for the extension versus load graph, which we can observe in the graph from 0 to 8. It is a straight line and after 8 it is being curved. So we can say the range of load is from 0 Newton to 8 Newton, which obeys the Hooke's law. Okay. Now B part, using information from this figure, determine the spring constant K of a spring S. So we know that spring force is spring constant K into X, that is F equals to Kx. So we can find K equals to F by X. So F by X we can take, that is we have to find out this F by X. So I have taken this point and these 2 points. So F 8 minus 0, that is 8, and X is at this point, X is, you can see, 15 centimeter, or in converted into meter it will be 0.15 meter minus 0. So 8 divided by 0.15. So we get the value of for K is 53.33 Newton per meter. And to convert into two significant figures by rounding off, we get 53 Newton per meter for the spring constant K using the graph. Okay. Now in the C part, a second spring identical to spring S. There are two identical spring. Second spring is this and this is they are of same material and the same. That is why it is written identical to spring S. Two springs are attached to the rod as shown. A load of 4 Newton is suspended from the bottom part. This is the load of 4 Newton. The arrangement is now in equilibrium. State the name of the form of energy stored in two springs when they are stretched. So we know that when they are stretched, the energy which is stored in the spring is nothing but the elastic potential energy. Now the second part, determine the extension of the arrangement in figure 2.2. Now we have to find out the extension in this figure. So as this spring S is identical and we have the graph for the load and extension, so we can say at 4 Newton, by looking at the graph, at 4 Newton the extension is 7.5 centimeter. Okay, fine. So at 4 Newton the extension on one spring is 7.5 centimeter. So there are two identical springs, so they will extend to the same. So it will be, total extension will be 15 centimeter for this arrangement. Now the load is carefully increased from to 6 Newton in total. Now from 4 to it is increased to 6 Newton. We have to calculate the distance moved by the load to the new equilibrium position as the load increases from 4 to 6 Newton. Now this is somewhat student got confused in this part. What you are supposed to do, you have to find out the gradient for the graph, that is in per 1 Newton how much extension is being there. So if we look out the graph, that is for per Newton. So for 8 Newton it is having 15 centimeter. So for 1 Newton it will be 15 divided by 8. So we get an extension of 1.875 centimeter for 1 Newton load of application. We have an extension of 1.875. Now the load is increases from 4 to 6 Newton. So the extension will be twice because it is being increased by 2 Newton. So for 1 Newton the extension is this. So for 2 Newton we have multiplied it by 2. So we get 3.75 centimeter. Now here we have two spring. So the distance moved to the new equilibrium position will be 3.75 into 2, which is 7.5 centimeter. Okay. Although it is of 1 marks, but you have to solve in this type. Now question number 3. In this figure 3.1, there is a trapped gas in the sealed end of the tube by a dense liquid. The scale marked on the sealed end of the tube is calibrated. This is the scale marked to read the volume of the gas trapped above the liquid surface. Shows the initial volume V1. This is the volume V1, which is 60 centimeter cube. The pressure of the atmosphere is 1.0 into 10 raised to power 5 Pascal, that is 1 atm. So the atmospheric pressure is also given to you, which is acting at this end because it is sealed end here. So no atmosphere is in contact with this end. So it is open end. So atmosphere pressure will act in this direction. State how figure 3.1 shows that the pressure of the trapped gas is equal to the pressure of the atmosphere. Now it is very simple. As you can see, the level on the both the ends of the tube are at the same position. So at the liquid, both the tubes are at the same level. So the pressure at this end will be equal to the pressure at this end, and we know that air only the atmospheric pressure is existing. So it is equal to the atmospheric pressure. Explain in terms of the momentum of its particle why the trapped gas exert a pressure on the walls of the tube. So we know that the molecules of the gas collide with the walls of the container continuously. There are gas molecules sorry, there are some gas molecules which are always colliding with the container continuously, and thus momentum of the particle are changes. They collide, they return back, so the velocity direction you can say is continuously changing. So we can say the momentum of the particle are changing with respect to time, and we know that force is nothing but the rate of change of momentum only. So a force is exerting by the air particles at the walls of the container, and per unit area if we calculate, that will be nothing but the exert the pressure on the walls of the tube. So you have to write this explanation in terms of momentum of its molecules. Okay. Now C part, more of the dense liquid is poured into the open end. Now we have poured more dense liquid at the open end. The level of the liquid surface in both the sealed and open end of the tube rises. Here also the level of the dense liquid rises, and here we have poured, so it is also rises it here. It is also mentioned in the question that temperature of the trapped gas and the atmospheric pressure both remain constant. They both quantities, that is the temperature of the trapped gas as well as the atmospheric pressure outside, are remaining constant. So in the first part, in the sealed end of the tube, the volume V2 of the trapped gas, we can see the volume of the V, the trapped gas is 50 centimeter cube, and in the open end of the tube the liquid surface is 15 centimeter. This is 15 centimeter above this level. Calculate the pressure P2 of the trapped gas. We have to find out the pressure in this trapped sealed end gas. So we know that as the temperature of the trapped gas and the atmospheric pressure both remain constant, so we can apply the ideal gas equation, that is PV equals to nRT. So this all remains constant if the temperature is constant. So P1 V1 is equals to P2 V2. P1 V1 is the initial pressure and volume, whereas P2 V2 is the final pressure and volume. So we have to find out the pressure P2. So P1 V1 upon V2. So we know that initial pressure was equal to the atmospheric pressure, which is 1 into 10 raised to power 5, and initial volume was given to us is 60. So V1 is 60 upon V2, we can see here it is 50. So just by putting up the values, we got the value of pressure trapped in the gas, this which comes out to be 1.2 into 10 raised to power 5 Pascal. Okay, now question number second part of this, calculate the density of the liquid in the tube. We have to find out the density of this dense liquid. Okay, for that we know that the pressure P2 of the trapped gas is equivalent to a point A, which is at the depth of 15 centimeter in the dense liquid from one end of the tube, plus the atmospheric pressure. Now what I have done is, I have taken an arbitrary point A, which is at the same level of the sealed end level, and which is at a depth of 15 centimeter from the free surface, or you can say the upper surface of the dense liquid. So I can say this pressure at this point will be equal to the pressure at A, that is the pressure by the trapped gas P2 will be equal to the pressure at point A. And we know that pressure at point A is nothing but the atmospheric pressure plus rho GH, that is pressure due to the dense liquid, where rho is the density of the liquid in the tube. So P2 we have already calculated, atmospheric pressure we know, rho we have to find out, G that is the 10 meter per 10 meter per second square, or you can say 10 Newton per kg. So we have taken 10 and H is in meters, that is 0.15. So just solving for density we get 1.3 into 10 raised to power 4 kg per meter cube. You have to calculate, you will get the answer. Okay, now the fourth question. A water has a specific heat capacity of 4200 joule per kg per degree centigrade and a boiling point of 100 degrees centigrade. What is mean by the boiling point? It is the simpler. Boiling point of a liquid is that temperature at which liquid is turns into the gas. At boiling point we all know the liquid is turning into the gas, or if we tell that we know that 100 degrees centigrade is nothing but for the water. So at 100 degrees centigrade water is converted into steam, that is the gas part of the liquid, water liquid. Okay, now the B part. The mass of 0.3 kg of water at its boiling point is poured into a copper container which is initially at 11 degrees centigrade. Now after few seconds the temperature of the container and the water are both at 95 degrees centigrade. Now what we are doing is we are pouring 0.3 kg of water at its boiling point, which is at 100 degrees centigrade, is poured into a copper container which is initially 11 degrees centigrade. And after some few seconds what we notice is the temperature of the copper container and the water both are at 95 degrees centigrade. Now what has happened here? The boiling point of the water which is at 100 degrees centigrade transfer the energy to the copper container. So the copper container raises its temperature from 11 degrees centigrade to 95 degrees centigrade, and the water loses its energy and decreases its temperature from 100 degrees centigrade to 95 degree centigrade. Now the first part, calculate the energy transferred from the water. So we know that E is nothing but mc delta T, where m is the mass, C is the specific heat, and delta T is the change in temperature. So just by putting the mass, C already mentioned in the question, delta T is the change in temperature for the water which is from 100 to 95. So we get the energy transferred is 6300 joule. Now in the next part, calculate the thermal capacity. Okay, please mention that thermal capacity of the copper container. So we know that thermal capacity is mass into specific heat, and so the formula E equals to capital C, that is the thermal capacity, into delta T. For the copper container the change in temperature is from 11 to 95, so the difference we have taken, and the energy is transferred by the water only, so it will be equivalent to 6300 joules. So it has absorbed the energy from the water to raise its temperature. So this energy will be equivalent to the energy transferred to the copper container. So that is why we have taken E as 6300 joule. So by solving we get the capital C, thermal capacity, as 75 joule per degree centigrade. Okay, in the third part, water from the container evaporates and the temperature of the remaining water decreases slowly. As we all know, in the evaporation the temperature of the water decreases. Explain in terms of molecule why evaporation causes the temperature of the remaining water to decrease. So we know that during evaporation molecules do certain amount of work to overcome the attractive forces. As more energetic molecules are likely to escape, those molecules which have more energy are likely to escape from the free surface of the water. So the average internal energy, if we talk of the remaining water molecule, will decrease, and this result in the decrease in the temperature of the remaining water. As the overall energy, internal energy is decreasing, that is only due to the cause of decreasing the temperature, which in, or you can see in another word, which will result in the decrease in the temperature. Okay. Now question number 5th. The distance between the center of a thin converging lens and each principal focus is 5 centimeter. There is a thin converging lens given to us whose focal length, or you can say the principal focus, is at 5 centimeter from the center of the lens. Describe what is meant by the principal focus for a thin converging lens. So, principal focus we all know is the point on the principal axis where the incident parallel rays after refraction or passing through the thin converging lens meets at a point, and that particular point is known as the principal focus. Okay. Now, the lens is used as a magnifying glass to produce an image I of an object O. Now, it is very important, it is being used as a magnifying glass. So, for the magnification, it is used for the magnification, we should note that the object is always in between the optical center, that is the center part of the lens, and the principal focus. So, in the first part, underline the terms that describe the nature of this image produced by a magnifying glass. So, in that case, we all know it is being enlarged, it is upright, and it is virtual. Do not consider the real and inverted, because that will not be the case for the magnifying glass. So, enlarged, upright, and virtual image are formed for the when the lens is used as a magnifying glass. So, now in the next part we have to draw the object. This is a full scale diagram of the lens of the image I. This is already given to us. In the first part, mark both the principal focus and label each of them as F. We know that this half, this is 1 cubic, half of this is representing 1 centimeter, and we know that principal focus is at 5 centimeter from the center. So, this is the center of the lens. So, this will be 1, 2, 3, 4 and 5. So, 5 at we have drawn the principal focus F on the either side of the lens. By drawing this, find the position object O and add object O to the diagram. So, what I have done is I have taken a straight line passing through the optical center or the center of the lens, which will have no deviation, and one line what I have done is I have taken which is passing through the principal focus and which will appears to meet at a point in the same side of the object, and then I have drawn according to the rules for the image formation with the arrows mentioned. So, I get an object between principal focus and the optical center, which is O, object representing the object. Determine the distance of object O from the center of the lens. You have to just to measure it. It will be 1, 2 and somewhat this will be 3. So, it will be 2.8 centimeter according to the scale. So, this is the image formation. Please note it down. Okay. Next, 6th question. The speed of sound in air is 340 meter per second, which is already given to you. Calculate the range of wavelength for sound that are audible for a healthy human ear. And we know that for a healthy human ear, the frequency range lies between 20 Hz to 20,000 Hz. And by the wave equation, the wavelength will be equals to speed of sound divided by the frequency. So, now putting the lower limit and the upper limit for the frequency, we get the lower limit for the wavelength and upper limit for the wavelength respectively. So, we get by just putting up the values, we get the answer. Wavelength range lies between 0.017 meter to 17 meter. Okay. Now, the B part, sound waves are longitudinal. Describe how a longitudinal wave differs from a transverse wave. That is the very common question. And we know the particles of longitudinal wave vibrates in the parallel direction of the wave travel. They are vibrating, the particles of the longitudinal wave vibrates in the direction of the wave travels, which comprises of rarefaction and compression, whereas the transverse wave vibrate in the perpendicular direction to the wave travel, which consists of the crest and the trough. Okay. This figure 6.1 shows a band in front of a building. The drum produces a low frequency sound. Other musical instrument produce a high frequency sound. And this you can see there are different types of instrument being played out. The drum is having a low frequency sound. Other all instruments are having high frequency sound. A young man at the side of the building hears the drum but not the high frequency sound from the other musical instrument. Explain why this happens. Okay, so we know that drum is having a low frequency sound. It means that it is having a longer wavelength, so gets easily diffracted as compared to high frequency sound which are having a shorter wavelength. So due to the diffraction phenomena, longer wavelength can easily get diffracted by the side of the wall, whereas the shorter wavelength are not diffracted. So the person can hear the more diffraction of the sound from the drum. Okay, question number 7 now. An electromagnet consists of a solenoid X that is made up of copper wire, and the solenoid contains an iron core. Explain why the structure of copper makes it suitable material for the wire. So we all know that copper contains free electron, and thus it makes a copper a good conductor of electricity, so it is more suitable material for making up of wire. Second part, iron is suitable material for the core of the electromagnet. Iron core is used for the electromagnet. Why it is suitable? So iron is a good magnetic material, we all know, and it also get magnetized and demagnetized easily. So we can say it is a temporary magnet. It becomes temporary magnet easily and also demagnetize easily. So that is the suitable material for the core of the electromagnet, because we want electromagnet in such a time that when we switched on the current, it behaves as a magnet, and we switched off the current, it behaves as a simple metal. Okay, shows the electromagnet inside the second solenoid wire. Now please look at this circuit. There is an AC power supply for the solenoid X which is coiled around the iron core, and there is a solenoid Y which is also coiled around this core with a larger turns, and the terminals of Y are here. X is supplied with an AC power supply. Now we have to describe and explain what happens in solenoid Y when solenoid X is connected to an alternating current power supply. Okay, we know that this solenoid Y is coiled around the X and this iron core. So there will be an induced EMF at the terminals of the Y due to electromagnetic induction phenomena, which is due to the change in magnetic field produced by the X. As the current is continuously changing in the X due to the alternating current power supply, so the magnetic field linked with the X is also changes, due to which there is an electromagnetic induction in the solenoid Y and an EMF is produced at the terminals of the Y. Okay. Now the second part, a switch and a lamp are connected in series with the terminals of solenoid Y. Now I have connected a switch and a lamp in series with the in between the terminals of the Y. When the switch is closed, the lamp lights up at normal brightness. Describe and explain what happens to the current in the solenoid X. You have to mention what will happen in the current in the solenoid X when I have connected a switch and a lamp between the terminals of the Y. Okay, so the current in the solenoid X will increase as to supply more power to the solenoid Y, which is being used up to light up the lamp. Because when you have switch closed, the current electromagnetic induction takes place and the current will pass through the between the terminals Y as the circuit is closed and the lamp will bright. Now it is continuously using the power. So to supply more power, the solenoid X have to increase the amount of current flowing in it. Okay, so the current in the solenoid X increases to supply the more power to solenoid Y for the lighting up the lamp. Okay, now question number 8. A power supply used in an electric vehicle contains 990 rechargeable electric cells, each of electromotive force, that is EMF of 1.2 volt. So we have a 990 rechargeable cell of EMF 1.2 volt. The cells are contained in pack. What we have done is, these are contained in some of the packets. With all the cells are in series, the EMF of each packet is 54 volt. There are number of packets and each packet contains an EMF of 54 in which the cells are connected in series. That you have to remember. Okay, now the first A part, calculate the number of packs in the power supply. So that can be easily calculated. The EMF of all 990 cells will be, each cell is having 1.2, so 990 will have 1.2 into 990, that is 1188 volt, and each pack is having a 54 volt. So number of packs will be the total number of EMF by 990 cell divided by each pack's voltage. So we get 22. So the number of packs which are having a voltage of 54 volt will be 22 in the vehicle. When in use, each pack supplies a current of 3.5 ampere. When the cells are being in use, so they are supplying a current of 3.5 ampere. Calculate the rate at which each cell is transferring chemical energy to electrical energy. So all cells are connected in series. So current is 3.5 ampere and EMF of one cell is 1.2 volt. So it is asking for each cell. So what we have done is, the rate of transfer energy is nothing but the power. So the power formula is V into I, where V is the EMF of one cell and I is also the current flowing through that cell. As they all are connected in series, so the current will 3.5 and a voltage is 1.2. So putting up the values, we got 4.2 watt, that is the rate of energy transfer, or you can say 4.2 joule of energy is transferring per second. Therefore 1 watt is nothing but 1 joule per second. Okay. Second part, the packs are connected in parallel to supply large current to drive the electric vehicle. Explain why it is necessary to use thick wire to carry this current. Now as they are connected in parallel, so the current will get sum up. So thick wire will have small resistance, so it will allow the current to flow through it. So thick wire will have a small resistance because resistance is equals to rho L by A, where rho is the resistivity, L is the length and A is the area of cross section. So we can say R is inversely proportional to area of cross section of the wire. So more the thicker of the wire, less will be the resistance. So thicker wire will have less resistance and hence will generate less thermal energy, because resistance creates, or you can say convert that electrical energy into waste and unuseful energy, that is thermal energy, by which the wire gets heated up or something like that. So there will be less risk of fire or insulation melting, over which the wire has some insulation melting. So if we have a small resistance, so it will have less thermal energy, so it will create less heat energy, and as a result there will be a less chance of risk of fire or insulation gets melt. Okay, now the ninth question, how a digital signal differs from an analog signal. You may draw a diagram. So I request all my students also that please, whenever you are supposed have an option or to draw a diagram, please draw it. So digital signal consists of only high and low values, or you can say low states or voltage. I have drawn V with respect to time, that is voltage and time. And analog consists of continuously varying voltage. So I have drawn this with respect to voltage and time. In the appropriate box, draw the symbol of AND gate and the symbol of OR gate. AND gate we have drawn, OR gate we all know, that is the symbol. State how the behavior of AND gates differ from that of a OR gate. So I always tell my student that AND gate refers to similar to the series connection and OR gates representing the parallel connection. What do I mean by this? It means that if in series connection I have a two switch, only the current will pass when these both are closed, and closed means 1 1. Okay, and in parallel, what happens if any of the switch is closed, current will pass through any of the branch. So if it will only not pass the current when they are open, it means 0 is 0. So open means 0 and closed means 1. Okay, so similarly I can say when both the inputs are different in the AND gate, different means either 1 or 0 or 0 or 1, then you gives the output 0 in the AND gate. And similarly, if these are the different in the OR gate, I get the output as 1. So that is the behavior of AND gate differs from the OR gate. Okay, I hope you get it. Okay, now in the C part, it's a very good question. There are some logic gates arrangement shown in figure 9.1. There are two inputs X and Y and two output P and Q. So for output P, the logic gate B has logic state 1 as high. Are you getting my point? For output P of logic gate B, the state is 1. So what we are getting is 1. So how the logic gates of the two inputs of the logic gate B will be, the upper input and the lower input we have to calculate. So in that case, what I supposed to do is I will do one by one. So I have taken 1 here, and let us take okay, fine, let us take 1 here and 1 here first. So here also I get 1, here also I get 1. So this is an AND gate. This is a AND gate. So 1 1 gives me 1 when there is a AND gate. So an AND gate will give me 0. So there I get 0, and if this is 1, I get 1 here, and this is NOR gate. Okay, so 0 and 1 gives me 1 in case of OR gate. So in case of NOR gate, I will get 0. So here this is not possible because we have supposed to get an output of 1. So this will not work. Now what I am doing is I will change it to, let us say, 1 here and 0 here. So this will remains the same. So if I get 0 here, then only there is a chance. Let us change the color so it will be understood. Sorry, here I have to take it 1. Okay, so if there is a 1, there will be no change. I will get the same 0 here. So in case of 0 here, I get 0. 0 and 0 OR gates give me 0, but NOR gates give me 1. So I am getting the desired output. So that will only happen when the upper and the lower input of B logic gate will have 0 and 0 input. So I have written out upper input and lower input as 0. You can try for others as well. If I take it, for example, if I take it 0 here and 1 here, or then see if there is 0 here, then I will get 1 here, and if it is 1 here, then again 1. So 1 1 I will get 1 in the case of OR, and in the case of 0 NOR I will again get 0, which will not be the desired output. So you can try any of the case. Now determine and explain the logic gate of output Q. So as for output P to be 1, so for P to be 1, what we have done is the two similar inputs of the NOR gate of A is 1 and 1, and lower input of the NOR gate of B is 0. Two similar, just wait, the two similar inputs of NOR gate A, this is not NOR gate, I have written it incorrectly, this is an AND okay, now it is correct, it is typing mistake. So two similar inputs of an AND gate of 1 A is 1 and 1, and lower input lower input is this of NOR gate B is 0. Okay, so here the red color one is the answer, so let us mark this. Okay, for output Q, upper input of Q, so for output Q the upper input is like this, that is Y is 0, so we can say this is 0 because this is the case for 1, so the same input will have for the NOR gate C. Okay, and the lower input is X and X is for the 1, so this is the answer. So here it is 1. Fine. So here for 0 and 1 we are getting for the NOR gate. This is also the NOR gate. So 0 and 1 for the OR gate we get 1, for NOR gate we get 0. So the output for Q is 0. So we have written output for Q is 0. Okay, you can try it, only this I have changes. Okay. Now the last question. This is a neutral atom of an isotope of element X. Give one similarity between this atom and a neutral atom of different isotope of element X. So what is the similarity in an isotope? That they have the same number of proton. Okay. Now in the B part, the isotope of element X is radioactive. It decays to form an isotope of element Y by emitting a beta particle. Please remember, it is emitted a beta particle. So we are used to nuclide notation for the isotope Y produced by this decay. So if X is going in beta emission, so X we can count the number of neutron, it comes out to be 13, and the number of protons, that is the atomic number, comes out to be 5. So the nuclide notation for X 13, that is the mass number, and here the atomic number, that is 5, going into the decay. So if it is a beta emission, so an electron is emitted, so a proton is converted into a electron and a neutron. Sorry, in beta minus, this is a beta minus, no? Okay, fine. So in that case, a neutron is converted into an electron and a proton. Electron gets ejected out and protons reside inside the nucleus. So the proton number gets increases by 1, and as a neutron gets converted and proton becomes, so the number of atomic mass number will remain same. So there will be no change in the atomic mass number, but where, or you can say the nucleon number of neutron plus proton will remain the same, but the atomic number will get increases by 1 as a proton gets increases inside the nucleus with an emission of an beta particle which is similar to an electron. So the nuclide notation for Y becomes 13 and 6. Okay. Okay, beta particle ionize the air they pass through less strongly than the same number of alpha particles. So there is a comparison between alpha and beta. Suggest why this is so. So beta particles are having less charge and less mass than the alpha particle. So we know that beta particle is electron and alpha particle is having a 2 times of positive charge. So there is a less charge in beta particle and less mass also. Electron is very lesser than the mass of an alpha particle, which is 4, or you can say having a 4 times of mass of an proton, which is much heavier than the a single electron. Also it has a high speed. This beta particle is having a high speed, thus get less time in air to ionize as they pass through it. That is the reason why they ionize less strongly than the same number of alpha particle. And alpha particle are having the highest ionizing power, then beta, and then at last we have the gamma. Least ionizing power is of gamma and highest is for alpha. Okay, that is all about for the 062541 May June 20 paper. Here we have done the complete solution for this series. I hope you have liked it, this video. If you like this video, please like, share and subscribe my channel and please share with your friends and classmates. Thank you.